It's a little bit over, but I hope that you, Vinit, will excuse that because now you are on with the ducted wind turbine revisited. Please, Dr. Vinit, Dighe. Well, how do you pronounce your name?
That's Dighe.
Dighe. Okay, good. Thank you. Okay, please go on.
If anyone can give me a thumbs up, like, can you see my screen correctly?
Yes.
Okay. So hello everyone, my name is Vinit, and this work what I'm going to present is part of my PhD in aerospace engineering, which was a couple of years back, like at TU Delft. Having said that, what I'll be touching into is the concept of ducted wind turbines, where I investigated the aerodynamics and the aeroacoustics of ducted wind turbines. And I'll slightly modify it just to suit our presentation for today, suiting ducted wind turbines for urban environment. So during the course of my PhD, I listed down a list of following questions, which could be addressed during my time. Some of which you can just see out here. The first one being what is the current scope of the ducted wind turbines in the market? How do I model the flow around the ducted wind turbines, both for aerodynamic and acoustic calculations? Having said that, what would be the optimal duct shape for a given configuration? And are there any further augmentation techniques or like any add-ons that could enhance the power in a certain way? And what would be the effect of unsteady and the yaw flow? As we see, unsteady flow conditions are very dominant in urban environment. So how would ducted wind turbines play in those areas? And finally, some conclusions and recommendations, which I would touch upon. So first, let's dive into the concept of ducted wind turbines. I guess most of you would be familiar with the concept of horizontal axis wind turbine. So on the left figure, what you see out here is a simple horizontal axis wind turbine, which is given by a stream tube model. And if you add a duct, so what a ducted wind turbine is, it just adds a duct around a simple horizontal axis wind turbine. And as a result of that, you see an additional lift force, which induces that additional circulation towards the trailing edge. And as a result, we see that additional mass flow being drawn into the turbine. And this is the result. We see the additional power being produced by a ducted wind turbine as compared to a horizontal axis wind turbine of the same diameter. I should admit that this is a very strong and a bold picture to put it out here, but this is very true. If you happen to simply Google a ducted wind turbine, you would see this is the real picture, as in several commercial attempts have been made so far to commercialize ducted wind turbines, but like it's not a huge success yet. So this was one of the driving force what led us to address some of my PhD questions, and here is the first one. So first I started investigating the very concept of ducted wind turbines from a numerical perspective of how to model the flow around a ducted wind turbine. So to this aim, I consider the very simple stream tube model. What you see out here is on the left is a simple bare actuator disc wind turbine. So what an actuator disc is, it mimics the pressure drop across the turbine. By saying that, you can model the thrust coefficient and the power coefficient of a horizontal axis wind turbine using a simple actuator disc theory. By adding a surrounding duct around it, you get this additional duct force. So on the figure on the right, you see this additional thrust force that is given by the duct, that is T duct in the figure. And we simply add this by using different methods, which I'll take you through the next slide. So this is the concept what we use for the preliminary investigation. Instead of using a real turbine, we placed an actuator disc model which mimics the turbine in this case. So my approach to this problem was using 3 different fidelity models. In this case, we used a panel method, so which is on the left. So this panel method simply calculates the aerodynamic forces on the duct and the actuator disc, which is a simplified version of the rotor, using a panel method which is based on the Euler formulation. So in that case, the mutual interaction between the duct and the actuator disc is inviscid, meaning that there is no viscous mutual interaction that is being accounted for. So this is a very simple method which takes roughly around a minute or so to finish, to get the calculations. Following that, like we can push these the results of these to a medium fidelity simulation, which for which we use a finite volume method based on Ran's formulation. We use a steady viscous calculations for the same, and because of that, we can use the mutual interaction. We can capture the mutual interaction between the duct and the actuator disc in this case. Having said that, it is computationally a bit expensive, so the runtime would be around 30 minutes in this case. And following that, we have the high fidelity simulation, which we use the very large eddy simulation based on Lattice-Boltzmann method. We use unsteady flow in this case to capture the viscous mutual interaction. And this is a very expensive simulation. As a matter of fact, the runtime would be around 7,200 hours for a single simulation. And this we use it on cluster. We run it on high performance computing. So coming on to the second question, what would be the effect of duct shape on the DWT performance? So like if you happen to see, like various commercial players have experimented with different shapes of the duct in order to enhance the performance of in order to enhance the aerodynamic performance. So this led us to try out a simple method which is based on a class transformation method. So the figure on the left is what you see is the black reference geometry is the reference geometry what we had from a commercial ducted wind turbine model. And what we do is we transform these using a parameterization technique to two different variants. So on the top, the blue region, the blue airfoil, what you see is a symmetric variant of the airfoil, and the red airfoil, what you see at the bottom is the cambered variant. So in doing so, we preserved the following geometric features. We did not vary the inlet area ratio. So meaning the inlet side was not touched upon, the exit side was not touched upon, and the inner side was not touched upon. So in a concise way, I meant to say is like the inside of the duct, what you see on the top part of the duct is not touched upon. Only the lower half is being played around by using parameterization technique. And in the figure, on the right figure is what you see, the 7 different variants of the duct shapes that we will be testing for different actuator disc configurations. So the first experimental campaign was conducted at TU Delft in the OpenJet wind tunnel facility. So what you see out here is a ducted wind turbine model, but as I said before, for the preliminary investigation, we replaced the rotor with an actuator disc. So the mesh, what you see inside the duct, is an actuator disc model. The probe that is being put from the back is a hot wire anemometer, which measures the velocity in the axial direction, but we also tested it for the radial direction. The figure on the right indicates the dots, which are the pressure taps. So we had 52 pressure taps along the surface of the duct, which would enable us to calculate the pressure coefficient along the duct surface for aerodynamic calculations. So these are some of the results what we had. We see the experimental results are in the black guys out here, and the blue is the panel method results, and the red ones are the Ran's method. An overall good agreement was seen with the numerical methods that we developed. A slight discrepancy was noticed on the right figure. If you see, the overlapping region is slightly moved in this case when it comes to the experimental values. The reason for this, we faced a couple of uncertainties during experiments. And this was majorly the reason, because there was a slight shift, but overall a good trend was captured, giving us the confidence in our simulations to proceed further. So the figure out here is the figures out here are very interesting. Like what you see on the left are the duct force coefficient, and on the right of the screen are the power coefficients for different duct configuration for the 7 different duct variants, what I showed you. What you will notice on the left side of the figure, the top quadrant is the figure in which you see the results of the panel method. So we on the x-axis, we have the different loading of the actuator disc. So simply saying that like different rotor loadings. And on the y-axis is the duct thrust force coefficient. What you would observe on the right figure is we see a slight overlapping in the trend lines on the bottom figures, and this is due to the viscous effect. So what we notice is like, yeah, camber does play an important role to enhance the performance, but after a certain limit, the camber behaves in a unsatisfactory way. And just to investigate that further, we have some flow field analysis. I'm sorry, are you able to see the screen, or is it just overlapping with one of the Zoom? You can see. Okay, perfect. So what I show out here is the 3 variants of the duct configuration. So D4, D5, and D6, which are mostly the cambered variants. What you would notice inside the rotor plane, inside the duct plane, you would see the region where you have a high velocity concentration or the additional mass flow that has been sucked. And the figure on the top, the figure on the extreme right would show that decreasing with the increase in camber. And this is the result because of the separation that you see in the blue region traverses from the lower part of the duct to the upper part. So this induces that additional flow separation inside of the duct, leading to the power drop. So definitely there were some of the learning takeaways when we started investigating what is the optimal shape of the duct that could be used for this. And what we could conclude is the performance of the ducted wind turbine could definitely be increased by increasing the duct camber. However, there is an upper limit for the camber, so beyond which the flow traverses inside of the duct, which leads to the performance drop. And a very interesting one was also the Lanchester-Betz-Joukowski limit, which sets the optimal power, rotor loading to 8/9 or 0.899 in a normal convention, is no longer applicable for ducted wind turbines. This value is lower. So what we noticed, we got an optimal rating for the thrust configuration for the thrust of the rotor, somewhere around 0.8, between 0.75 and 0.8. So having said that, like the next question was, we have a good performance, we have a good performing duct. So is there a way where we can further improve the performance of the ducted wind turbines? And to this aim, we started, we had a second experimental campaign in which we tested our system with a small micro tab or a gurney flap fitted at the edge, fitted at the trailing edge of the duct. So the C figure, the figure C is, if you notice, there is a 2% chord length of the gurney flap that has been attached to the trailing edge of the duct. And we tested this for both the configuration, carried out the experiments for both the configurations using the radial and the axial measurements for the flow for the velocity. What you notice out here is the axial flow velocity with the gurney flap. On the left figure, I show the axial velocity, the center line. On the right is the radial measurements. Definitely with the gurney flap, you see an increase in the velocity with respect to the no gurney flap configuration. And this matches well with the experiments as well. If you notice at the flow field analysis, we did some flow field analysis using Ran's calculation for this. I show the normalized velocity contours in this with no gurney flap and with 2% gurney flap on the at the bottom. So if you look at the figure, bottom left figure carefully, within the rotor plane, you would see that additional mass flow or the additional red region being as compared to the upper part, as compared to the upper figure. This is the result of the gurney flap, which is attached to the trailing edge, which enhances the recirculation effect and throws that additional mass flow into the turbine plane. We also tested this, we also extended our study for using, trying out the multi-element ducts. So there was this experiment conducted by Professor Igra at the Israel Aircraft Industry in 1981. So he tested two configurations in which a ducted configuration with an actuator disk model and a and a second element, which is just like a second airfoil attached to the trailing edge of the duct. And how would that enhance the performance? But the question to us was, if we have the second element, what would be the optimal setting, or what would be the optimal position of the secondary element with respect to the primary duct? Having said that, we parameterize the study using two parameters, which are zeta and theta. Theta represents the angle of attack with respect to the duct configuration, and zeta is the radial gap that we need to have between the primary duct and the secondary element. So these are the figures what we get from the flow field analysis. If you see the first figure on the left shows me the results of the panel method, and what I show out here is the contours of R. So R is the augmentation ratio, which is simply the power increase with respect to the original turbine, with respect to a no duct configuration. So with respect to the panel method, you don't, the blue region doesn't appear in this as compared to the Rance method. So the blue region, if I can just highlight that region, is the separation region, which is not being taken into account using the invisit panel method. And just to show you some results of how the flow field looks like, the panel method on the top for the bare without the multi-element duct, the one for the panel method on the left and the Rance method on the right, for the two different configurations of the parameters that we investigated. So we noticed that, and with the increase of theta, there is a performance drop, but with an increase of zeta, there is a performance increase. So there appears to be like a sweet spot somewhere, which gives me an optimal performance for the multi-element duct configuration. So it's just like you need to have some optimization study before trying out different configurations. So the learning takeaways from this were the gurney flap or the multi-element duct, which would be retrofitted to improve the aerodynamic performance of DWT, would strongly depend on the installation settings of the secondary element, that in this case was the gurney flap or the secondary duct, with respect to the primary duct element. So having said that, like this was one of the important questions we highlighted when it comes to performance of the system in an urban environment. So in an urban environment, you see a lot of unsteady and yaw flow conditions with respect to like when you don't have a yawing system for the same. So how would these guys, or how would these systems perform in these unsteady conditions? So taking the learnings from the previous experiments and the numerical study, we built a complete 3D model of the duct. In this case, the actuator disc now is replaced by a real rotor. The same is being tested in the open jet wind tunnel facility. So where it's a massive facility in which we can capture the velocity and the pressure across the duct as well, and also do some measurements like PIV, which I won't be touching out here, but keeping it more concise. So just for the numerical validation, we quickly tested our the large eddy simulation results. It matches really well if you notice it closely, there is a bump or a drop in the experimental values, which is simply because of the noise damper, which I point out here, which is not modeled in the simulations, which I show hereafter. So these are just to check the yaw insensitivity. We tested the two configurations now. One is my original, the Donchi turbine, and the second is the D5 model, which is one of the cambered variant of the duct, which we came up with. What you'll notice out here is the interesting figure is something on the right. If you see the column for the 7.5 degree, for the baseline case, the Donchi case, you would see the vortices break down when you implement a yaw condition, which is not true when it comes to the cambered airfoil. So this gives us a confidence that yes, ducted wind turbines, if designed in the correct way, could be insensitive to a yaw up to a certain yaw angle. So we tested the same for the azimuthal variation of the radial velocity across the turbine plane. And this is what I show you. There is a slide on the figure on the right. You would see that the Donchi D5 version would show a velocity rise in comparison to the baseline case. As Mohammed also highlighted, like putting turbines in urban environment or in a city-like environment would be challenging when it comes to the noise regulations. So this is what we tested upon. We tested like with using 72 virtual microphones. We calculated the overall sound pressure level for the two cases, the Donchi and the Donchi D5 case. We definitely see a higher noise for the cambered variant of the ducted wind turbine model. We plotted this with the PSD just to check what would be the reason, just to differentiate between the broadband and the tonal frequency. So we definitely see that the broadband noise is something that is dominant throughout the case, which you see on the figure on the right. So the blue region out here shows like a broadband region, and the red one is for the Donchi region, for the Donchi turbine. So what we thought was, so just to conclude, what was the reason of the noise was definitely the turbulent flow structures which are convecting along the surface of the duct, which enhances or grows higher in comparison to the baseline case, what you see on the right, with a cambered variant. So just to wrap it up, it would be like with a cambered variant, you could definitely increase the aerodynamic performance, but at the same time, it would cost you some additional noise. So definitely some learning takeaways from this was DWTs demonstrated yaw insensitivity up to a specific yaw angle. However, it depends, the yaw insensitivity, however, depends on the mutual interaction between the duct and the turbine, which changes with the duct geometry, turbine configuration, and the yaw angle. And also what I showed you in the last slide, the duct shape has a strong effect on the acoustic performance of the ducted wind turbine model. I did have some recommendations, which I chalked it down. The most interesting one I thought was, the first one was, it is recommended not to use ducts with very large ducts or ducts with very large duct area ratio. So this would definitely add up to the heavy load what you see in the urban environment, and which is not optimal for the performance. And the wing and ground effect is very rightly studied for aircraft propellers, but not touched upon for the study of ducted wind turbines. So having a roof-mounted wind turbine, so what I show you out in the figure is a pictorial representation of a ducted wind turbine on a rooftop in the city of Delft, where I finished my PhD. So it's a typical scene what you see with a cathedral and canals out here. If the wing and ground effect would be very good to investigate whether this would be like an optimal condition to play around with respect to the ducted wind turbine configuration. So thank you everyone for your attention, and thank you for taking out some time to listen to my talk.
Thank you very much, Vinit. think it's been really interesting. It's time for some questions, if there are any, or comments. Of course, you just have to digest the speech, presentation. So, but as for the other presentations, we will make a follow-up later on.